but to some degree there was a match between this extension of stable models to propositional formulas, because there's just such a kind of a nice, we get such a nice simple mathematical definition, and the extensions to the language of answer set solvers that was invented by programmers who just found these extensions convenient. And I'll give a few examples showing how these two things match each other. So one thing that answer set solvers can do, they work with disjunctive rules. So they can write P or Q, for instance, and with Q denoted by this vertical bar here. We need ASCII characters, right, when we deal with programs. And for this program, this is the output that will be produced by an answer set solver. And if you look at the corresponding formula P or Q in logical notation and apply the definition of a stable model, you will see that these are indeed two stable models according to our definition. If you look at this example, you may think that this disjunction from the point of view of stable models is exclusive disjunction. The set consisting of both P and Q, making both P and Q true, is not stable. But actually it's not quite the case. In this case it is exclusive, but if you extend this program a little and add these two rules, saying that P and Q are equivalent to each other, then an answer solver will say both P and Q are true. It does not have to be exclusive. So it's a little different. This formula can be also translated into, this input program can be represented this formula in the syntax of propositional logic, and if you take this formula and apply the definition of a stable model to it, it will justify this answer. Another invention of programmers around 1999, I think, was they invented something called choice rules. If you write P and Q, for instance, in braces, what answer set programmers say is that this is a choice rule which says choose arbitrarily which of the atoms P and Q you want to include in your stable model. Any combination of choices is okay. So for this input, this is the output produced by an answer set solver. It will say it's okay to make both of them false, or Q false and P true, or the other way around, or to make both of them true. And choice rules can be viewed, if you want to relate this construct to propositional formulas, you can think of that as a combination of two laws of the excluded middle for P and for Q. If you take this formula, that's how we, so we can think of this program here, this choice rule, as the conjunction of these two excluded middle formulas written in logic programming notation. This is a formula which will have exactly these four models. And this is the last example of this kind I think I wanted to show. This is a program which consists of two rules. The first of them is the choice rule that we saw before. And the second is almost like a prologue rule, except that it does not have anything in the head. You see this if arrow and nothing to the left. And rules of this part with the body but without the head, they're called constraints. And this is also, its choice rules and constraints are actually used in answer set programming even more often now these days than standard prologue rules. What this rule says, it says intuitively, you should drop from the collection of stable models that you formed from the rest of the program those stable models that violate the constraint, in other words, that satisfy the body of the rule. So if you look at the output of an answer set solver for this program, it will produce 3 rather than 4 stable models out of the 4 that we saw in the previous slide for this choice rule. One is missing here, the one that makes P true and Q false, because this is what is not allowed. So you can think of this negation symbol in this case. And that's how we would write this program in propositional logic notation. This constraint at the end is essentially the formula representing the body with the negation symbol in front of it. And this use of constraints is justified by this general fact that is not difficult to check, that if you have a conjunction of f with something that begins with negation, the stable models of this conjunction can be characterized as the stable models of f that satisfy this additional constraint node G. Generally, if you take the conjunction of two formulas, the stable models of the conjunction are not related to stable models of individual formulas in any simple way. But if the second formula begins with negation, then we have what you would naturally expect from classical monotonic logic. And that's because of this simple monotonic behavior of constraint, they play an important part in programming. Now let's go back to the distant past that turns out to be related to the study of stable models. At this point, we're going back to 1932, not yet to 1930. 1932 is when Gödel, in his note that about intuitionistic logic, in which he proved that intuitionistic logic cannot be represented by a finite number of values, he introduced this family of intermediate logics called GM, where M is an integer greater than 1. In this logic GM, the truth values are numbers, integers between 0 and m minus 1. Conjunction and disjunction are minimum and maximum. And let's actually concentrate on negation. This is an interesting thing. Negation works in such a way that the truth value of the negation in Gödel's logics is one of the two extreme values. It's either 0 or m minus 1. It can never negate, negation of a truth value can never give you anything in between. So for this reason, it is different. This is, I think, the main difference between Gödel logics and Mel's favorite clean logics. Clean logic is, it satisfies the double negation formula. And these are really intermediate logics between intuitionistic and classical. Because of this thing for negation, the double negation cannot be eliminated. So it's really moves us a little closer to intuitionistic logic. And G2 is classical logic. And G3, it was introduced actually in Heitmann's paper, in which he introduced intuitionistic logic in 1930. The reason why he introduced this in addition to intuitionistic logic is he wanted to prove that intuitionistic logic is indeed weaker than classical, that you cannot prove the law of the excluded middle using only axioms of intuitionistic logic. And this was his argument. He gave these truth values, truth tables for what is now called G3. And he showed that this three-value logic satisfies all postulates of intuitionistic logic, but the law of excluded middle is not true, so that was his argument. And he commented on this third truth value, which is 1 in this expression. He said that intuitively denotes a proposition that cannot be false, but whose correctness is not proved. That's kind of was the intuition. But basically, G3 was a technical tool for him. And one way to axiomatize G3 was to take axioms for intuitionistic logic and then add this axiom schema, which is weaker than excluded middle, so it does not give us full classical logic, but it is just a little bit stronger than what's called weak excluded middle for formulas beginning with negation. G3 is known under many names. One of them is called, also has this wonderful name, the logic of here and there. Because if you look at it from the point of view of Kripke models, then you can describe it by models with two worlds only. And if you call this the here world and the there world, then it's a logic of here and there. So this is in other words, what we want to do if we want to describe G3 in terms of this models. We look at pairs of sets of atoms, so that the first is a subset of the other. And the definition that you see here, the definition of satisfaction, is exactly the definition of satisfaction for Kripke models for intuitionistic logic, except that instead of arbitrary partially ordered set, we look at this one set with two worlds. And to see how this is related to our three-valued view, if you take such an interpretation, a pair XH, XT, and take an atom, one of three things can happen. Either the atom belongs to both XH and XT, or it belongs to XT but does not belong to XH, or it belongs to neither. These are your three truth values. And now, this is the remarkable discovery that Peirce made in 1997. That's a paper that I mentioned before when we talked about intuitionist logic. What David Peirce invented is what he called equilibrium logic, which turned out to be very closely connected and essentially equivalent to this idea of a stable model. If you take an HT interpretation, in other words, a pair of sets, what Peirce defined is when it is an equilibrium model, he said, of a propositional formula F. And his definition goes like this. An equilibrium model, first of all, it should be what we call the total interpretation, that is, the two parts should be equal to each other. The truth values in the here world and their world should be the same. So that's the first condition is that this X repeated twice satisfies our formula in the sense of definition that's on the previous slide. And the second is a minimality condition. It said if you modify the first element of the pair, the here world, in any possible way, and the possible ways are replacing by subsets, because otherwise the condition that the first set is a subset of the other will not be satisfied. F will not be satisfied. In other words, the X as the truth assignment that we chose for the here world is minimal for our F. This is what he called an equilibrium model. This concept is actually similar to John McCarthy's concept of circumscription, which was also based on the idea of minimality, except that McCarthy worked with models in the sense of classical logic, and Peirce extended this idea to the next best thing, to here and there, two worlds rather than one. And it turned out what David proved in 1997 and Paolo extended in 2005 is that stable models and equilibrium models are the same thing, except that equilibrium model is repeated twice because we refer to what happens to this one. And what I said about the relation of stable models to intuitionistic logic at the beginning immediately follows from this fact. We can say even more. If the equivalence of two formulas can be proved in G3 in the logic of here and there, not necessarily intuitionistically, they will have the same stable models. Simply because if your two formulas have the same HT interpretation satisfy them, then of course with this addition the equilibrium models will be also the same. So what we see from this is that if the G3 is the main mechanism that we need for checking the strong equivalence. If you want to prove that two formulas are strongly equivalent, prove the equivalence in equilibrium logic, in G3, excuse me. And it turns out that the converse is true also. So that strong equivalence is exactly the equivalence in G3. So that's how this technical device invented by Einstein in 1930 turned out to be a very useful technical device for something that was invented 67 years later. And here's my conclusion. And one thing that I didn't mention yet, this last sentence here, the only examples of programs that I showed here were programs without variables, although I used variables in previous at one point. But answers that solvers, just like Prolog, can also process programs with variables, and that if you want to study their semantics and stroke equivalence of programs with variables, which is a practically important question, then we have to study G3 extended to first order logic, and this is something that a lot of work that was done on more recently. Thank you for your attention.
Questions?
Could you just clarify something? Is it true that every satisfiable formula has a stable model, or?
No. For instance, the formula P, if not P, is satisfiable, but it has no stable models.
What are the programming languages that are used to create set solvers?
Well, they are written in conventional languages in the same in which you write efficient software, and C++, I guess. I must say that just as with set solvers, there's a whole industry, and there are competitions held every 2 years where they give this, when they measure which solver does this in 10 minutes and which one in 9 minutes, and they're very proud they get it in 9 minutes. So they, that's a kind of work. The nice thing about this work is that people in particular, this group in the University of Potsdam and many others, they are, as I understand, first-class programmers because they win in competitions. And also they are people with good mathematical taste. So it's for a logician, it's a pleasure to talk to them. And I think that's why they create this wonderful software. One other thing about kind of the degrees of sophistication of these set solvers that I can mention is that 2 or 3 years ago, the creators of Klingo decided to participate in the SAT solver competition. And the thing is that even though their software is designed for a different purpose, for finding stable models, but you can apply it to a very special case of clauses. Clauses can be, if you want to find a truth assignment that satisfies a set of clauses, you can encode it as a logic program of a particularly simple form. Or else you can take the code that they have for their answer set solver and drop some parts of it and use a simplified version. And they won in some competitions in comparison with set solvers. In some tracks they got the first place. So even by the standards of set solvers, these systems are very good. And it's a pleasure to see this, that we have these excellent programmers and the programs that they write interesting to logicians. More interesting, I would say, than Prolog programs, because with Prolog programs, it's really painful exercise to find, and Mel knows this better than anybody else, to find some logic that matches what they do. And here, those 4 lines that I showed you. Well, there are some complications, but I will not talk about them.
So G3 is the logic that characterizes strong equivalence.
Yes.
And G3 is an intermediate logic, a logic between reductionistic and classical logic. There is a classical result of Maximova. There are, I believe, 7 intermediate logics which satisfy interpolation property, similar to Craig's. What else is known about the logic G3? Is G3 one of these logics with interpolation property? And are any other special properties known for that logic?
I think it is. First of all, it does have the interpolation properties, as I remember. But the main thing special about G3 is that out of all intermediate logics, it's the closest to classical. It has almost two values, just three. Three is the next number after two. So it's as classical as you can be if you want to be slightly less classical. Slightly closer intuitionistic logic.
In just two worlds, instead of one. Two worlds, but
I remember once I talked about G3 in the presence of Johann von Bentham, and I said that it's amazing that what we learned from intuitionistic logic, where the excluded middle plays a special role, is important for the study of logic programs. And he said, why do you mention intuitionistic logic as a source of this information? I mean, G3 it's almost classical. Intuitionistic logic has nothing to do with this, and I have to admit this because I think 3 is a lot closer to 2 than to infinity.
I have another question.
Yes.
So is the stable model existence problem, is it feasible? Are these algorithms complete? Do they always work? And is it in P, or is it the existence of a stable model, is that in P complete?
For programs, kind of Prolog-like programs, conjunctions of rules, it's NP complete. The problem existence.
Or even a stable model?
For state, yeah. So it's in the same complexity class as satisfiability. If you look at arbitrary propositional formulas, it's in the second class of the polynomial hierarchy. And algorithms that are used for them, including those that are used for arbitrary propositional formulas, they are in principle complete. That is, in principle, they always terminate.
In the middle of your talk, you mentioned another super-intuitionistic logic, but you didn't say anything about its properties. You don't know what the logic is precisely, or?
This other GM?
Yeah. No, not GM. Earlier in your talk, you mentioned.
I didn't mean to talk about anything
Other
than
than
G3
GM.
actually,
That's
yes.
okay.
Yes.
That's
So I
what
said,
I was wondering.
yes,
Okay.
yes, yes. I said there's this concept of strong equivalence,
Okay.
and it is intermediate, and at the end,
Okay.
what I tried to say is that strong equivalence is exactly equivalence in G3.
G3, okay.
You don't need anything else.
Nothing else.
well, I think we're ready for a coffee break. And let's thank the speaker.